Okay, any questions before we start? About the homework, about the things that we were doing? I mean, the idea of the homework is so that you practice and you learn. I mean, it's not, the point is not just to give you some grades. So if there are any questions you have about the homeworks, we can discuss it. You can correct your homework.
Hocam bir tek son soruda yani direkt o enerjisi bir Schrödinger, Glanzbek'te bir Schrödinger denklemi bekliyordum zaten de gelmesini. Sizin hatırlamıyorum ben şimdi tabii öyle 5 gün oldu. Ben türevleri şeyden bağımsız kabul etmedim. Fiziklerden. Öyle olunca da integration bypass yaparak buldum şeyi. Hareket denklemlerinin farklı şeyler için, fiiller için. Fiil hız için yaptığım zaman fiil bulmam gerekiyordu. Fiil için yaptığımda fiil hızı bulmam gerekiyordu. Bu konuda kalan karıştı da bir başta sonra tamam.
You resolve it fine. I mean, I think there is a mistake in the question, by the way. The action should have been this one. The reason why you get a zero energy Schrödinger equation is that I had given you this equation. If you want to get the time-dependent one, you just add the time derivative here. This action would give you the time-dependent Schrödinger equation. So the idea was mainly, I mean, okay, we are calling it field theory, etc., but we are not really doing anything very different than quantum mechanics. So even ordinary quantum mechanics is somewhat included in this description. You can obtain the Schrödinger equation in this description. Okay, if we would just make a short review of what we were doing last week, I mean, we had left in the middle. Now, the idea was, now we have an interacting system. So basically we have, if you consider the Hamiltonian, there is a part which we know how to solve. And there is another part which we don't know how to solve. So H0 is a system which we can exactly solve, so we know everything about that system. But when we add the V to it, we are having problems. So what we are trying to do is we would like to separate, I mean, given a system, the system will evolve under H0 anyway. There is an evolution due to H0. This evolution will be modified due to the presence of that potential, or in our case, it will be interactions between the particles. So we would like to separate these two evolutions. And at the end of the day, we will always be interested in calculating matrix elements of this form. As a function of time. And as a function of time, this matrix element is actually this one. These are some initial and final states. They are fixed states. So if you would consider the Schrödinger picture, the states will evolve. So what we do we were discussing the so-called interaction picture, which kind of separates the evolution due to H0 and says that our operators evolve under H0. So we define the interaction picture operators as e to power I H0. Let me call that T minus T0. There is some reference time T0 where we know the states. We know the states at the time T0. We calculate the matrix elements of certain operators and see how those matrix elements evolve in time. So the operators evolve under this H0. And so if you look at the matrix element that we are interested in, it just becomes ht minus t0 e to power minus I h0 t minus t0. Here we have the interaction picture operator at the time t. And then we have e to power I h t minus t0. e to power, no, this is h0 minus I h0 h t minus t0 psi I. So the operators themselves are evolving with h0. What remains, all this expression, is what we call the evolution of the state in the interaction picture. In the interaction picture, at the time t, this is defined as so if v is 0, for example, the states do not evolve. So we basically go to the Schrödinger, the Heisenberg picture. If v is 0, h and h0, they are equal, so that operator appearing over there is just the identity operator. And this operator is what we call u of t, t0. And we had shown that u of t, t0 can be actually written as a time-ordered product of the integral of the potential or the interaction. Okay, this is not actually a solution. This expression look over there doesn't really help us much, except it's a short way of writing what this u is. And then we said that, okay, so if we have our interaction picture operator state, at some time t, this is also evolved by an operator that we called ut2 t1, and this ut2 t1 is actually just like the ut0. It has this form, but this time the limits are from t1 to t, which is also the same thing as if you look at over here. It is slightly modified form of this one. This is t2. This is t2 t1 e to power minus I h0 t1 minus t0. So if t1 is t0, this t1 is t0, we basically recover the previous expression anyway. So this is the Schrödinger picture. I repeat, the idea of, interaction picture. I repeat, the idea of the interaction picture is to separate the evolution due to the potential and the evolution due to the so-called unperturbed Hamiltonian, which we can exactly solve. And then we said, okay, so we have all these tools, now what do we do with them? So eventually what we will be interested in, for example, one case we will be interested in, let's say, we will create a particle at some point, let's call that x0, at some time. We create our particle. Omega is what we call the vacuum, the ground state. It's not necessarily the empty state, it is the state that has the minimum energy. We create some excitation on this state. And then this is, let's say, this we create at the time, at some time, let's call it t0. In the interaction picture, there is this reference time which we are free to choose. We can just choose that time. And then we let this state evolve in time. We already know what the evolution of an arbitrary state is, up to time, let's say t1. And now we would like to find the amplitude that we have a particle at some other point at the time t1. Well, to calculate that amplitude, we just take the inner product with the final state. This is at the time t1. So this was where we had left. So this is what we would like to calculate. Or at least we would like to be able to make an expansion of this in terms of v. Now there are a couple of things we have to do. First, here we have the operators phi x1, phi x0. We have to first convert them into our interaction picture operators. Now, how do we do that? Well, we know the relation between the operators in the Schrödinger picture and the operators in the interaction picture. This is how they are related. So that matrix element I can write as, let's say, omega. If I invert this, any operator can be written as e to the power minus I h0, t minus t0, or I t e to the power I h t minus t0. So this I will, since this is the state I'm looking at some later time t1, I would like to express it in terms of OI t1. h0 t minus t0, I h t minus t0. I have e to the power minus I h t1 minus, this is t1. t1 minus t0. This is h0. And then this is the reference time, so when t is equal to t0, the interaction picture operator and the Schrödinger picture operator, they are essentially the same. Well, you see, this is nothing but what we call u of t1, t0. Well, here I have the h0 acting on omega. No, okay, no, that will stay as it is. So this is what I have. So the matrix element that I'm interested in can be written in this form. Now, what about omega? Let's calculate what omega is. You see, omega is the ground state of H. So, and we also have this state 0. Now, this 0 state, which is the eigenstate of the theory with V is equal to 0, we can use the identity basically because this is the identity operator, the resolution of identity in terms of the eigenstates of the H0. Let me just separate out omega that I'm interested in. This prime just means that I'm ignoring the ground state in that sum. The ground state is already taken into account in the first term. Well, the general trick to extract the ground state, in fact, for any system, would be just let your system evolve in imaginary time. Now, what does it mean? Well, let me just evolve my system. This will be e to the power minus I e omega t plus sum over the remaining states. Now I will take the limit as t goes to infinity. But you see, all those terms, all those exponents, they are highly oscillating in that limit. I would like to suppress some of them. So to suppress them, I take the limit as t goes to infinity, but with a small imaginary part. So what happens in this case is e to the power minus I, let's say e of t. This becomes limit as t goes to infinity of e to the power minus I e of t minus epsilon E of t. So as t goes to infinity, due to that the first term in the exponent is oscillating, but the second term in the exponent causes suppression. As t goes to infinity, epsilon, eventually we will take the limit as it goes to 0, but we first take the limit t goes to infinity. So all the terms, all those exponents will actually go to 0. But the exponent with the smallest power, with the smallest prefactors, smallest en, will go to 0 more slowly than the other ones. So at that limit as t goes to infinity of 1 minus I epsilon e to power minus I h of t 0 is equal to the limit as t goes to infinity, if you like, minus I epsilon e to power minus I e omega t omega 0, or the ground state is actually equal to this one, limit as t goes to infinity times 1 minus I epsilon e to power minus I h of t 0 divided by e to power minus I e omega of t This is the ground state of the full theory. In fact, if you are able to, let's say, numerically calculate the time evolution of any state, this is a means of obtaining the ground state of that system. This is nothing but the time evolution by a time capital T. If you are able to evaluate the time evolution numerically, just put all these things over there, all those, calculate its time evolution for a long enough time. Of course, on the computer you cannot take the time t goes to infinity, but you can pick up a large enough time. If you have a large enough time t, then all the higher states will die away and you are left with the ground state. This also allows you to calculate E omega of t. Because you see, if you don't put the correct number E omega of t over there, when you take the limit either diverges or just goes to 0. So you should choose a value, you should just try many values of E omega of t, because if you don't know the ground state, you don't know its energy. Just take different values of E omega of t, calculate this limit numerically, and if that, for the value of E omega of t, that gives a finite limit, then that is the energy of the ground state, and the state that you obtain as a result of the time evolution, you get the ground state. Now, this imaginary trick, let me just give an interlude. This imaginary time trick is quite often used in statistical physics. You see, in statistical physics, what do you want? You want to calculate the partition function for a given system. Do you remember the partition function? It's just the sum of e to power minus beta en, sum over all the microstates. And if you know the partition function, you basically can calculate anything you want about the system. But this is nothing but sum over n, e to power minus beta h, n. But you see, this is nothing but the trace of e to power minus beta h. Anyway, let's look at this one. But you see, if you set beta is equal to I times t, then the partition function is just the trace of e to power minus I h of t, or t is equal to minus I times beta. So if you calculate the evolution operator in quantum mechanics, if you put an imaginary time in that evolution operator, you get the partition function in statistical physics. If you know the partition function in statistical physics, just put an imaginary beta. And you get the time evolution operator in quantum mechanics. Although those two subjects seem to be quite unrelated with each other, they are closely connected. Both real-time evolution in quantum mechanics and statistical physics. Okay, that's not our problem. Let's just go back. Let me change this slightly. Well, t goes to infinity or t0 plus t goes to infinity, they are the same thing. H0 acting on the zero state, we define the energy of the zero state to be 0. So this is just 1. This is the same thing. Well, do you remember what that operator is at the top? That is the evolution from minus t to t0. So this is our omega. So now we are able to express omega in terms of the empty state, which is not necessarily the ground state. Well, we can do a similar thing to calculate the bra of the ground state. Well, the bra of the ground state will be, well, just look at this expression over there, this line. So it's vacuum e to power I h t divided by e to power I e omega of t 0 omega, limit as t goes to infinity 1 minus I epsilon. I'm not just taking the dagger. You see, what I'm actually doing is, okay, I have this I still have this expansion. I still multiply the bra 0 with e to the power minus I h t. Now, if I have the plus I h t over there, I should take the t goes to infinity of 1 plus I epsilon. They will essentially you should give me the same result. But I would rather keep it as 1 minus I epsilon in both limits. For the time being, it's just a mathematical trick. You see, the motivation for this trick is this one. You see, here we have this expansion. And when we do that expansion, we would like to suppress all the higher states and we would like to have only the ground state. So that expansion should go to 0. Those contributions from the higher excited states should go to 0 faster. And they should all go to 0, but they will go to faster. So that's why we insert this I epsilon. Now, another way of looking at it would be this one. You see, what is u of t0 minus t? Time ordered product of e to power minus I integral from minus t to t0 of v of t prime dt prime. Now, we are essentially setting the lower limit to a slightly imaginary value. Now, if you calculate limit as t goes to infinity 1 minus I epsilon vi of t, this will also go to 0. It should go to 0, if I'm not wrong. But if it goes to 0, it just basically means that at far minus infinity, we turn off the interactions. So at minus infinity, there is no interaction. The ground state is the empty state. Then we turn on the interactions slowly. Eventually, they will come to the full power. Now, have you seen the adiabatic theorem? So what is the adiabatic theorem? So the idea is essentially this one. So let's say you have something in your theory, in your system, that changes slowly. One example would be, one simple example, consider the particle in a box with a size L. Your L will be a function of t. Then you have the initial state. Let's say the initial state is your ground state. But this time, of course, the ground state will depend on R, the position. And as a parameter, it will depend on your L, its initial value. Now the question is, what is the state of your system as a function of time? The adiabatic theorem tells us that, what the adiabatic theorem tells us is, if, in this case, L, or whatever parameter you have, changes very slowly, at the time t, your system will still be in the ground state corresponding to the value of that your parameter at that time. Well, of course, there will be also an evolution due to the energy. Let's say energy of the ground state is 0 for all that. So if your state starts in the ground state and you change your parameters slowly, your system stays in the ground state, corresponding to the new parameters. So here basically we are doing essentially the same thing. At t goes to minus infinity, there is no interactions, the potential is 0. And we know the ground state, no particle state is the ground state. So we slowly or adiabatically turn on the interactions. So the system will, of course, will change, its ground state will change. Nevertheless, since you are turning on the interactions slowly, the system will always stay in the ground state of whatever system you have. So for example, this is a method that is also used in some quantum computation, quantum computers. So what you do is you adjust your system such that the ground state is the solution that you are looking for. Then you start from a system, you have your system, you can tune the interactions in your system. And you first need to determine what should be the interactions if the ground state is to be your solution to your problem, whatever you are trying to solve. Then what you do is you start from a set of interactions whose ground state you already know. You create your system in that ground state, and you slowly change your interactions. Eventually they are equal to the interactions that you want. And then you know that the state has evolved to the ground state with those interactions. That should be the technology used in quantum computers called, I think they are called adiabatic quantum computation. Or this, I don't know if you have heard of them, D-wave. So essentially we are also doing the same thing over here. Now we have this thing over here for the bra. You see, the reason why I would like to calculate the bra separately is, let's go back, let's go over here. This is essentially what I would like to calculate. Now I wrote this ket as an evolved state. It's the evolved state from the empty state up to a time t0. Then I evolve the system from t0 to t1. I have the other operator at t1. And now here I would like to have an operator that is evolved from t1 to infinity. That is what I'm looking for. Now this will be equal to limit as t goes to infinity 1 minus I epsilon 0 e to power, let's say, e to power minus I h t minus t1. I would like to insert an e to power I h0 t minus t1. Taking t goes to infinity or t minus t1 goes to infinity, they are the same thing. And h0 acting on this vacuum, it gives me 0. Divided by e to power minus I e omega t minus t1 0 omega. This is my omega ket. Now I can combine everything. Okay, let's go, let me go back. This was what I am interested in. And now we have this ket, which is, okay, I will write the limit later on. Okay, what we first did was we wrote this ket as, okay, where was it? Okay, this is the first step we have. This is the first step. Then we had calculate those ground states. Let me look at the bra first. I will not write the limits. Just keep in mind that eventually I take the limit as t goes to infinity 1 minus I epsilon. So the vacuum e to power I h0 t minus t1 e to power minus I h t minus t1, e to power minus I h0 t1 minus t0. Then I have OI of t1, u of t1 t0, OI of t0. Then I have the ket. The ket is over there. This is u of t0 minus t0. And I have in the numerator 1 over e to power minus I e omega t0 minus t omega 0. And I also have from the bra e to power minus I e omega t minus t1. So this is the complete expression I have. Now look at this operator. Does that look familiar? That is nothing but u of the evolution from t1 to t. So that is equal to u of the evolution from t1 to t, or I of t1, the evolution from t0 to t1, or I of t0, and the evolution from minus t to t0. Divided by e to power minus I e omega t0 minus t omega 0 squared e to power minus I e omega t minus t1. So I have the 0 state at t equal to minus infinity. Then if I evolve it up to time t0, then at the time t0 it is already the ground state of whatever theory I have with the full interactions. I create my particle at the time t0. Then I let my, at the time t0, at this is, okay, this is not O, this is phi. Phi dagger x0 t0. And this is phi x1 t1. I create my particle at the time t0 at the point x0. Then I evolve my system from t0 to t1. And then I check if there is a particle at the point x1 at the time t1. I annihilate the particle, let's say. And then I let my system evolve up to the final time t, which is at infinity. And at t equal to infinity, I turn off my interaction slightly. It's now my ground state, my empty state, not the ground state, ground state of the free theory. And, well, let's see. And remember this u, ut1, t2. This was defined as the time-ordered product of e to power minus I from t1 to t2 of v in the interaction picture t dt. So let's see. All the operators appearing in that operator, the evolution from minus t to t0, they are at the time between minus infinity and t0. Then I act with an operator at the time t0. Then I act with operators between the time t0 and t1. Then I act with an operator at the time t1. And then I act with, this is t1. Then I act with operators from t1 up to infinity. You see, all the operators appearing in that product, they are already so-called time-ordered. In use, the operators are already time-ordered. The various terms that are multiplied, they are already multiplied in time order. So the whole thing is time order. So that is equal to a huge time ordered product of phi I of x1 t1 phi I dagger of x0 t0 e to power minus I dt from minus t up to capital T of vi of t. This is the numerator. Now what I did in the numerator is, since I already wrote everything under a time ordered product, the ordering is fixed by the time ordering itself. I can just change their orders. I change their orders such that all the u's are multiplied together. So u, and just note that u, there was a property of u, T3, T2, T2, T1. This is just u of T3, T1. This is a general property of the u itself. So that is why I ended up having this exponent over there is just the product of all three of the u's. Now there's still the problem of the numerator. Whatever the numerator is. Now to calculate the numerator, we can actually do a trick. Let's look at this one. The normalization of the vacuum. There are no operators. Phi's are just identity operators, if you like. Well, then this would be just 1 over n time ordered product of e to power minus I minus t to t dt vi of t. But the ground state, you can choose any normalization you like. The convention is to usually use 1 as the norm of the ground state, the ground state. So we know what n is. So what we had actually shown now is phi x1 e to power minus I h t1 minus t0 phi x0 is actually equal to the empty state. You see, this is the ground state. This is the empty state. They are not necessarily the same state. Time ordered product of phi in the interaction picture at x1 t1 phi x0 t0 e to power minus I from minus infinity to infinity vi of t dt. Well, with this slightest epsilon. I mean, they go to infinity with small imaginary parts. Divided by just the exponent. Now, why we are really interested in this matrix element to start with? Because essentially whatever you would like to measure, eventually we will be able to express them in terms of such matrix elements. Everything we can measure will be related to such matrix elements. And all of those matrix elements we can calculate in terms of the empty state matrix element of some time ordered product. Now, how does this help us to obtain an expansion in V? Well, you see that if the potential is small enough, there is an exponent over there. We can expand the exponent, and each term in the exponent will contain higher and higher powers of V. If V is small enough, you can just truncate it, and you get an expansion in terms of the interactions in your system. So that will be basically the idea of the perturbation theory we have. Well, from now on, I will drop the I. because essentially I will exclusively work in the interaction picture. That's why I will be dropping that I over there. So phi of x1 e to power minus I h of t1 minus t0, phi dagger of x0. This will be in the interaction picture x1 t1, in the interaction picture of x0 t0. This is the first term, plus the first correction to this term will be, for example, minus I dt zero time ordered product phi I x1 of t1. Now I'm dropping the I. Phi of x0 t0 v of t plus all the higher terms with the 1 over the other matrix element. Of course, we also need to expand that denominator also, if we would like to get an expansion in terms of v. So there are essentially two things that we need to do. For example, in this case here, we just have the two fields at different times. There's their time-ordered product, and we take their empty matrix element. That we can actually calculate now. Then when we are going to look at the interactions, for example, in our Lagrangian, we can have dt v of t would be d for x, let's say a lambda divided by 4 factorial phi of x to the power 4. This is a possible interaction term we will study. So here we have not just 2 fields, but 6 fields under a time-ordered product. Then the next question is, how do we calculate the time-ordered product of 6 fields? Now the simplification will be, whenever you have such many fields, you have the multiplication of many fields, you are looking at their time-ordered product. There is a theorem called the week theorem, which allows us to calculate the time-ordered product of many operators in terms of the time-ordered product of 2 operators only. Now, before giving a break, let's just look at this two field or 2 point time-ordered product. Let's calculate that. So let's look at phi of x1, phi dagger of x0. I switched to the 4-dimensional notation, that's why I'm not writing the time explicitly here. Well, we had already calculated phi of x. If you remember the expression, it was the d4k divided by 2 pi to the, no, d cubed k, sorry. 2 pi cubed, 1 over square root of twice omega k. And now we had phi of k e to power minus I kx. And now we had phi dagger of k e to power I kx. And here kx is omega k x0 minus k dot r. This was the expression for the field. This is already time-dependent field that we calculated in the Heisenberg picture, but this is the Heisenberg picture with h0 only. This is how the field evolves in time, taking into account the h0 only. Well, that is our interaction picture actually. So this is, I don't need to do anything else. I already know the field, I just need to calculate the time-ordered product. Now, what was the definition of the time-ordered product? Well, time-ordered product basically tells me that whichever operator has an earlier time, move it to the right. So this is if x10 is larger than x00, it is phi of x1, phi dagger of x0. And if it is the other way around, if x00 is larger than x10, that is, if the operator at x0 acts later, well, it should act later, it should move to the left. Now, in this example, we have a real field. Since we have a real field, phi dagger is actually phi. So this will be equal to, yeah, let's keep it like this for the time being. And then we will see how things will change. Or, let's not keep it like that, but let me just rewrite it slightly. This is phi of x10 minus x00. Plus 1 minus. You see, theta x is 1 if x is larger than 0, 0 if x is less than 0. Theta of minus x is 1 if x is less than 0 and 0 otherwise. So if you just sum them up, the sum is just 1. Either one of them is 1 or the other one is 1. It depends on how you define what happens when x is equal to 0. Well, sometimes you can define x when x is equal to 0. It's conventionally defined to be a 1/2, and this relation still holds. So I can just write my time-ordered product as, I'm just rewriting the second term. So the time-ordered product just becomes theta x10 minus x00 times the commutator. And then I have the plus this is the time-ordered product of two fields. Well, we can just go ahead and calculate this commutator first, and then calculate the second one next. Well, okay, I again changed my mind. Let me just start with the initial definition. Let me just use this definition, the first line. Now I want the ground state, the empty state matrix element of phi of x1, phi of x0. Well, this will be, in both phi's I will get an integral, d cubed k1 divided by 2 pi cube, d cubed k2 divided by 2 pi cube. Then I have 1 over square root of twice omega k1, 1 over square root of twice omega k2. And then I have the vacuum, phi of k1 e to power minus I k1 x1 plus phi dagger of k1 e to power I k1 x1. Then I have phi k2 e to power minus I k2 x2 plus phi dagger k2 e to power I k2 x2 and the vacuum. Now, of course, this is what I have if x10 is larger than x00. In the other case, I have to change the order of those operators, so I would get 0, phi of k2 e to power minus I k2 x2 x0, sorry, plus phi of k2 dagger e to power I k2 x0, phi of k1 e to power minus I k1 x0, plus phi of k2 dagger, now k1 x1 e to power I k1 x1 vacuum. So I just use the definition of the time ordering product. Now, of course, I have to make multiplications, but keep in mind, not all the terms will contribute, because I have the vacuum state. For example, let us look at a typical term over here. I have a single state. If I take this term and this, sorry, this is the empty state. This is the annihilation operator. It annihilates a particle. It lowers the energy. But it cannot do that. And hence the contribution from that term is 0. Because phi k acting on the empty state just gives me 0. That is how we define the empty state. Similarly, phi dagger over here acting on the bra gives me 0. So there's no contribution from there. And similarly over here, this phi term doesn't contribute, and this phi dagger term doesn't contribute. So quite a number of terms do not actually contribute to my sum, to my matrix elements. Now, what is left? D cubed k1 divided by 2 pi cubed, d cubed k2 divided by 2 pi cubed, 1 over square root of twice omega k1, 1 over square root of twice omega k2, step function x10 minus x00, and I have the 0, phi of k1, phi dagger of k2, e to the power 0, e to the power minus I k1 x1 e to the power I k2 x0. This is the first line. Then I have plus theta x00 minus x10. And what is left inside is phi of k2, phi dagger of, no, sorry, this is k1, phi dagger of k1, e to the power minus I k2 x0, e to the power I k1 x0. Vacuum. Well, let's continue. D cubed k1 divided by 2 pi cubed, d cubed k2 divided by 2 pi cubed, 1 over all these factors, then I have the step function, then I have the 0, phi k1, phi dagger k2. I can replace that product by the commutator. When I replace that product by the commutator, I'm essentially subtracting the term in which those two operators are just exchanged. But when if I exchange that phi k1 and phi dagger k2, then phi k1 will be acting on the empty state, which is 0. So when I'm replacing those products by their commutators, I am actually subtracting 0, which doesn't change anything. I do the same trick in the other one. Do you remember what those commutators were? 2 pi q q k1 minus k2. So basically I can evaluate, let's say, the k2 integral using those Dirac deltas, and I will be left with a single integral. Let me just call it k. 2 pi cubed 1 over twice omega k. I have theta x10 minus x00 e to power minus I k x1 minus x0 plus theta x00 minus x10 e to power I, this is I k2, this is x0, k1, x1. I k x1 minus x0. Yes, that's what I end up having. Okay, this will be minus I k omega k x10 minus x00 plus I k dot r1 minus r0 plus theta x00 minus x10 e to power I omega k x10 minus x00 minus I k r1 minus r0. Now, I will make a change, a slight change. In the second term, instead of k, I can just put minus k. The sign over here will change. Omega k will not change, so those parts of the exponents will be the same. I will have e to power I k dot r1 minus r0. Then I will have theta x10 minus x00 over omega twice omega k e to power minus I omega k x10 minus x00 plus theta x00 minus x10 divided by twice omega k e to power I omega k x10 minus x00. Okay. Did you understand what the trick I did? Just to, the exponents, they look quite different. They don't look very different, but there are sign differences in the exponent. That is, some of them, I'm just trying to collect those terms. I can make a change of variables so that one part of the exponent will be identical. In the second term, I just replace the k vector, the 3 vector k with minus 3 vector k. It doesn't affect anything except then the sign. So when the sign changes, both factors have the same exponential. I factor it out. This is what I end up having. Now here I will do one more trick. Let's remember some complex calculus. And use the residue theorem. So what does the residue theorem tells us? It says that on the complex plane, if you are integrating over a closed contour, then the result of the integral is just the sum of the residues multiplied by 2 pi I. That's what the expression of the residue theorem is. Now, how will I use that? Well, there are various tricks that you can use the residue theorem to evaluate integrals. For example, if you have a real integral along the real line, you can just consider the real line as the real axis in the complex plane, and then the integral along the real line, you can convert it to a contour integral by just closing your contour along the upper complex plane or the lower complex plane. Now, depending on your integrand, either the upper complex plane or the lower complex plane, the large arc in the upper or the lower complex plane will not contribute. So let's look at this one. dk0, 8 power minus I k0. Let me just call it x0 for the time being. It's just a number for the time being. Divided by k0 squared minus omega squared. Let's try look at this integral from minus infinity to infinity. Now, why do I consider this integral? This integral essentially has two poles. If I consider the complex k0 plane, if x0 is, let's say, positive, then to get a finite answer, I have to close my contour from the lower half. No, yes, from the lower half. This is if x0 is larger than 0. If x0 is less than 0, I have to close my contour through the upper half plane. Now, it has two poles. At k0 is equal to plus omega, and k0 is equal to minus omega. These are the poles. Well, the integrand written in this form is not really well defined. So I have to shift these poles slightly in the complex plane. Well, I have various choices. For example, I can shift both of them towards the upper plane. If I shift both of them in the upper plane, the resultant integral will be 0 if x0 is larger than 0. Because if x0 is larger than 0, I have to close the contour in the lower half. When I close the contour in the lower half, there are no poles inside my contour, so the result is 0. Or I can shift the poles, both of them, downward. Then if x0 is less than 0, the resultant integral will be 0. Or two other choices is shift one of them up, one of them down, or the other way around. So it's up to you. We will determine which one suits our purposes. Now let me calculate the residues. Now there is a residue when k0 is equal to omega. And how do I calculate? It's a first order pole. So this residue at k0 is equal to omega will be the limit as k0 goes to omega of k0 minus omega multiplied by e to power minus I k0 x0 divided by k0 squared minus omega squared, which will be e to power minus I k0, no, not k0, omega 0 x0 divided by twice omega. There is another residue. The residue at the pole when k0 is equal to minus omega is limit as k0 goes to minus omega. This time it is k0 minus omega, e to power minus I k0 x0 divided by k0 squared minus omega squared, which is e to power I omega 0 k x0 divided by twice omega. No, omega 0, omega. So these are the residues. Well, let's go back to the integral that I'm interested in. The result. This is the result I'm interested in. This will be equal to theta x10 minus x00. You see, the first one is the residue of my integral. This one at k0 is equal to omega. The second one this one over here is actually the residue when k0 is equal to minus omega k. Well, this essentially tells me that this is nothing but the integral dk0. Of course, I have to divide by 2 pi I, because the residue theorem tells me it's just the result of the integral is 2 pi I times the sum of the residues inside my contour. E to the power I k0 x10 minus x00 divided by k0 squared minus omega k squared. But keep in mind that if x1 is larger than x0, if this is positive, so this is my k0 plane. If x10, was this the integral I considered? No, I had the minus I. Okay, so this is the minus I. Now, if x10 is larger than x00, I'm closing my contour through the upper half plane, right? Yes. And if x10 is less than x00, I'm closing it from the lower half, if I put the minus sign over there. So I want the residue at k0 is equal to omega k if x10 is larger than x00. So this is the position of one of my poles. This is the position of the other pole. So the poles are actually at k0 is equal to plus or minus omega k plus I epsilon. These are the positions of the poles. Let me just check to make sure that I'm not making a mistake. If x10 is larger than x00, this is positive. No, it's the other way around. If x10 is less than x00, this is negative. If this is negative, I k0 has a positive imaginary part. So when I'm multiplying it, I should add a positive imaginary part with infinity, imaginary number. So it should be plus I, so I'm closing in the upper half plane. Okay. So the poles are actually the other way around. So the poles are at these values. k0 is equal to plus minus omega k minus I epsilon. So the denominator over here, I can actually write, okay, so k0 squared minus omega k squared is actually 1 over k0 minus omega k minus I epsilon k0 plus omega k minus I epsilon. So that I'm actually shifting the poles. Exactly. You see, there is an overall minus sign. Overall minus sign that already makes it plus I epsilon. So the poles are actually at omega k minus I epsilon and minus omega k plus I epsilon, as you pointed out. So if I factor the minus, okay, so that is nothing but 1 over k0 squared minus omega k minus I epsilon squared, which is 1 over k0 squared minus omega k squared plus 2I epsilon omega k. But remember, epsilon is eventually, I'm taking the limit, epsilon goes to 0. So epsilon omega k is actually going to 0. So if you like, I can just rename all of this thing as I epsilon. So this is 1 over k0 squared minus omega k squared plus I epsilon. Omega k is a constant as far as k0 integration is concerned. Okay, so let's go back. Now we were interested in this expression over here. This was equal to d cubed k divided by 2 pi cube. You see, we had obtained this result over here. E to the power I k r1 minus r0. And all the remaining parts in that integral, with all these step functions, 2 omega k's, etc., they are just this integral over here. Of course, with the understanding that we add a minus I epsilon. Let's see, this plus I epsilon. We first evaluate this integral with non-zero but small epsilon, and then set epsilon equal to 0. So this is equal to, well, this is essentially now a 4-dimensional integral. 2 pi to the 4 e to the power minus I k x1 minus x0, and minus I divided by k0 squared minus omega k. Remember, it was just k vector squared plus m squared plus I epsilon, or this is equal to d4k divided by 2 pi to the 4 e to the power minus I k x1 minus x0 minus I divided by k squared minus m squared plus I epsilon. This is so-called the propagator. Now, why is it called the propagator? Well, it essentially tells us the amplitude for a particle initially at the space-time point x0 to be at the space-time point x1. So, I mean, that amplitude is non-zero only if the particle can move from x0 to x1 or propagate from x0 to x1. And that plus I epsilon is important in that expression. That is what defines this integral. You see, here, when we were discussing this integral, depending on how you shift your poles, the value of the integral changes. And what we obtain is the expression we actually need, which is this given by this expression over here, is actually obtained when you shift the poles in this manner, one below the axis, the other one above the axis. That is what we need. And that can be calculated by putting a plus I epsilon in the denominator. Any questions? Let's give a break, 10-minute break, and then we will continue.